Okay, so we've looked at an awful lot of instrumentation now. So getting back to our P&ID. They don't use LEDs, they have to use a filament bulb because you can't be sure that an LED is working. An LED can still pass current while not working, so I wouldn't use that. So here's back to our P&ID drawing. And I've put on the instruments. Now, everything I'm going to do the control with lives inside a PLC. So here's all my controls inside the PLC. Now I'm just going to add all the arrows that join everything together. Think. Now as you can see, this P&ID drawing is now useless. It's just a bird's nest. It doesn't tell me anything. So I need something a bit more useful, and this is where the other drawing system comes in useful. Here is the function block drawing of the weight control. And what we have here is an inner loop, which is the dough flow. And we have an outer loop, which is the basis weight loop. And the basis weight loop is outputting a set point to the dough flow control. So this is what we have. Now I have a few specific problems with this. My first specific problem is that there's actually a massive delay between when the stuff comes out of the extruder to when it ends up at the scanner. So in my case, I'm going to say I have a 25-minute delay. What that means is that it takes 25 minutes for the donuts to get from the extruder to the scanner. So that's a bit of a problem, and I'm going to go through how I'm going to get over that problem. Some other problems I have is that the thing I tend to use for controlling is P&ID. P&ID is a crock of shit. So I'm going to try and find some better control solutions than P&ID. One of the best control solutions I'm going to do is float my output. Floating my output means P&ID outputs an absolute valve position. If you have a set point of this and a process variable of that, P&ID outputs 57.4% valve position. Floated control, on the other hand, what this works like, this works much more like the way you control stuff when you get in a shower. When you get in a shower, if it's too hot, you don't say to yourself, oh, the valve is 14.5% open, I will open it to 15.3% and that will cool it down. You say to yourself instead, oh, it's a bit hot, I'll open the cold tap a bit. So you open the cold tap a bit. You don't keep track of where the valve is. P&ID keeps track of where the valve is. Floated control doesn't keep track. That's why we say it's floated, because it doesn't give a rat's where the valve is. It just says, oh, it's a bit too little, I'll open the valve. It's a bit too high, I'll close the valve. That's how floated control works. Another problem we have with P&ID is we're not achieving what's called bumpless transfer. You see, if you're starting up your machine, what the operator does is he puts the flow loop in manual and he opens the valve. Then he waits until it settles a bit, then he drops it into auto. Now, if you have normal non-floated P&ID on that, what P&ID will then do is say, oh, I need to open that valve. If you've especially got a very small proportional gain and a very large integral gain, such as you would have if you had a slow-acting system, then what P&ID will do is shut the valve and start opening it again. Now that's going to cause a bump, which will almost certainly totally upset the flow. What we would prefer to do is what's called bumpless transfer. Bumpless transfer is when the P&ID, instead of saying, oh, I know what to do, I know best, and shutting the valve, what the P&ID says is, okay, I'll work with where the valve is now. So instead of just shutting the valve totally, I'll change the valve by small amounts from where it is now. Floated control, of course, because floated control doesn't keep track of where the valve is, it just opens the valve and closes the valve. Floated control naturally gives you bumpless transfer. So here's how it would look in the case of normal P&ID and floated control. So here's the operator, he comes along and he opens up the valve, he overshoots a little bit, and then he corrects, and the valve is now tickling along quite nicely, and the flow is more or less where he wants it. So he quickly pushes the auto button to put that control into auto, and P&ID does its stuff and completely screws up the whole flow, because it says, oh, I know better, I'm going to shut that valve. Floated control, on the other hand, does bumpless transfer. So the operator comes along, opens the valve, fiddles with it a little bit, gets good flow. He then hits the auto button, and it very smoothly controls the valve, brings us nicely into set point, no nasty bumps. So there's two things we've looked at. Bumpless transfer is the first thing we've looked at, and floated control. Another thing I want to look at is history arrays. This is how we're going to get around the problem that there is a 25-minute delay between the extruder and the scanner. We're going to use history arrays. Now, the idea of using history arrays has only been around for a very short time, say 50, 60 years, really, since we started using computers to control. So I'm going to use a structure, a memory structure in the computer, which is called a FIFO structure. FIFO stands for first in, first out. So a first in, first out structure. I'm going to put my values into my FIFO structure, and I'm going to use that for the control. And now my basis weight, when my basis weight control is making decisions as to what sort of output to the flow set point, it's going to make decisions based on a historical value. Not on a now value, but a historical value. Because as each value is pushed into the FIFO, it shoves the next one along. So they gradually move along. So that this one here is the value that was 25 minutes ago. Now that, maybe I've lost some of you there, so I'm going to go through that in detail slowly. Okay, here I've got my machine, and I'm just starting up. Thank you. I'm just starting up. My flow loop has just been put in auto. I've colored it green to indicate it's in auto. So my flow loop is in auto. The operator is running with a set point of 50, which he knows is vaguely where he should be. He's guessing. It's based on previous experience. He's guessing he should have about 50 litres per minute of dough to get. He's looking for 100 gram. Here's my basis weight set point, 100 gram donuts. The basis weight control is in orange. It's in suspend. It's waiting. So I've got 50 litres per minute of dough. My valve's about 30% open. I've got nothing in my FIFO structure because I haven't made any donuts yet. And of course I haven't read any weight because I haven't made any donuts yet. Okay, this is how it's going to work. Dunk. There's my first donut. My first donut was made with a flow of 50 litres per minute of dough. So 50 litres goes into the FIFO structure. So there's my first donut. I'm very proud of that. A little while later, dunk, My next donut comes along. My first donut moves down the conveyor. Now during this time, the flow just dropped off to 49 litres. The valve is opening to compensate, so that 49 goes into the FIFO structure. And the 50 moves along one step. So the 50 moved along by one. Now a little while later, bump, a new donut comes out. My flow has returned to 50, so 50 is put into the structure, so that 50 goes in there, and all of these move along by one. My basis weight is still in suspend because I still don't have any donuts to measure. So my basis weight is doing nothing. It's sitting there with its thumb up its bum. Dump, another donut. Now this donut came out, the flow had just risen to 51. The valve is just closing a little bit off to compensate for that. So that 51 is stuck into the structure and all the rest shift along by one. Dump. Oh look, this one. Another donut's come out. This one over here's got cooked. So this donut's got cooked. It's coming out nice and cooked. And this one was made at 50 litres. 50 goes into the FIFO structure and everything shuffles along by one. As you can see, what's happening is the FIFO structure is essentially tracking the donuts that correspond to it. Dump. Another donut comes out. Once again, this one was made at 51. That goes in there. Everything shuffles along one. Basis weight still on suspend. Dump. Another donut comes out. This one was made at 50. That goes in there. Everything shuffles along by one. Basis weight still in suspend. Now, dump. Aha! A donut has arrived at the scanner. The scanner reads that donut and it says, oh, you're 95 grams. I want 100 grams. So the weight control says 95 grams isn't enough. I need to increase the set point to the flow. Now, I'm going to increase the set point by 5 litres per minute. But I'm going to increase the set point by 5 litres per minute based on what the flow was at the time of making the donut. So at the time of making the donut, according to the FIFO structure, the flow was 50 litres a minute. I need to increase it by 5 litres a minute, so I'm now telling the flow to increase to 55. And that's the value that we have up there, 55. I'm increasing the flow to 55 litres per minute because I think that that would be the correct flow. Does everybody understand that one? Okay, so, donk. The next donut arrives. The scanner reads it and says, oh, your weight is 94 grams. I need to increase that flow by 6 litres a minute. But 6 litres a minute based on what the flow was when you were made. And when you were made, the flow was 49. So 49 plus 6, I need to increase that set point to 55. So it sends a new set point of 55, which, luckily enough, was exactly the same as the last time. So, donk, the next donut arrives. This one is at 95. It then goes through the same decision. 95, I need to increase by 5 based on what it was when you were made. So 50 plus 5 gives me 55. That's the new set point. Next donut arrives. This one weighs 96 kilograms. It says, okay, I need to increase the flow by 4. 4 plus what the flow was when you were made gives me 55. So I output a set point of 55. Next donut arrives, and then once again it outputs a set point of 55. And then the next donut arrives and a set point of 55. and the next donut arrives. Now this time, it's saying, oh great, 100 kilograms, I'm bang on. So I need to increase the flow by 0 litres a minute. I'm going to maintain the set point of 55. So this is how I get round the very long delay. Okay, now John, you're asking, if it's a very long process, would you use a second scanner? Yes, you would. If it's a very long process and it's very expensive, what you do is you have a second scanner up here at the hot end to measure the weight and moisture. And that scanner sends predictive results in, so that would be much quicker. So that if this scanner is weighing, the weight here of course will be not exactly the weight, the final weight, because the weight at this end will be on uncooked donuts. So you can do some predictive control and thus minimize the amount of bad product made. But you can't be absolutely certain you're going to get it right because of the fact that the scanner at the hot end, sorry, the scanner at the uncooked end is not the final product. So what we end up with is 2 scanner loops. We have an inner scanner loop, and then we'd have the main outer scanner loop, which would be supervising the inner scanner loop. So with very, very long processes, yeah, we might have anything up to 4 scanners down the length of the conveyor belt. And each scanner could be predictively an inside loop inside the main outer basis weight loop. Does that answer your question? Okay, because you've got to bear in mind that with some of these machines, such as paper machines, they can be easily 25, 30 minutes long, and you don't want to make 30 minutes a bad toilet roll. Okay. So looking at this type of control then, this is what the moisture control will look like. Moisture control, once again, we're using the makeup moisture. So we have an inner flow loop, we have an outer loop. Now this outer loop works on what's called water weight. So it's actually measuring the grammage of water, how many grams of water there are in the donut. And then we have at this end a ratio control. Now it's the ratio control I want to talk about. Here we have, I'll do with a better pen than that. Ratio control. Ratio control is used extensively where we're mixing this and we're mixing that, or mixing lots of things in different ratios. Now in this case, my ratio target is 10% moisture. That's my ratio target, 10% moisture. I'm making 100 gram donuts. How many grams of moisture? What is the water weight set point? If I need 10% moisture, 100 grams. Yep, you've got it, 10 grams. Now, the reason why I'm doing 10% moisture is because since I have now very, very good and tight moisture control, my customers have said that they want 9% moisture plus or minus 1%. Now 9% plus or minus 1%, to me that says 10%. 10% moisture. I want to put as much moisture as possible in my donuts. Any idea why? Water is a lot cheaper than dough. So I'm going to put as much water as I possibly can in. The more water I can sell them, the better it is for me. And that's one of the things you can do once you've got very tight control systems working. That's one of the reasons we sell this stuff. Okay, here's my cooking control. I've got 3 loops, one inside another. My inner loop, oh, I didn't want to do that. My inner loop is the steam pressure loop. Oh, I did it again, would you believe? Okay, so my inner loop is steam pressure. My next loop is oven temperature. That's the first level of supervision. My next level of supervision is my color control. I want to control to a certain color. We are driven by color, especially when it comes to food. We want things to look glowing. One of the ways we can judge whether breadstuffs is fresh or not is whether it looks dull. If it looks dull, then we say it's not fresh. So particularly with foodstuffs, we like them to be glowing. In fact, we actually like things to be artificially glowing. So what we do with paper, for instance, paper is naturally a sort of a yellowy colour, and cotton is naturally a yellowy colour. With paper and cotton, what we do is we add what's called, oh, I didn't want that. We add what's called fluorescent whitening agent. Fluorescent whitening agent. And what fluorescent whitening agent does is, here's a bit of FWA. It takes UV and outputs blue. If you make things look blue, they look whiter, they glow. So basically, fluorescent whitening agent takes UV and changes it into bluey white. Fluorescent whitening agent is the powder you get inside of fluoro tubes. So that powder that you get inside of a fluoro tube is a type of fluorescent whitening agent. So we want our donuts to be a nice colour. So we want them to have been cooked properly, and we also, just as an aside, we want them to have the correct amount of fluorescent whitening agent in them. I didn't put that in, but we would also have fluorescent whitening agent additives coming in. Now you might say to yourself, oh, surely we wouldn't be adding this to food. Well, oh, surely we do. They actually inject, in some countries they inject fluorescent whitening agent into meat to make it look redder. In the United States, they inject carbon monoxide into meat to make it look redder. Now, carbon monoxide is that poisonous gas that if you breathe it in kills you. But, you know, as long as it looks right, that's okay, eh? Now, I've got some other little problems with my controller, with my dough machine, with my donut machine. Every time I change the moisture, I affect the weight, because when I make it wetter, it looks a bit different as it goes through the oven. So every time I correct the moisture, I mess the weight up. And every time I correct the weight, I mess the moisture up. So I'm getting this happening. This is my weight and this is my moisture. My set points are here. That's set point, set point. Whenever the weight corrects, the weight corrected there, but whenever the weight corrects, it screws up the moisture. And so the moisture goes along bad for a while and the moisture corrects. But whenever the moisture corrects, it screws up the weight. And then whenever the weight corrects, it screws up the moisture. And then whenever the moisture corrects, it screws up the weight. This waveform that we see in trend plots, this is called a trend plot. Trend plot. This waveform that we see in trend plot is called a crenellation waveform. Crenellation. Crenellations are the things on the top of a castle. They're crenellations, and this waveform looks like a crenellation. So when you get this crenellation waveform on your main measurement values, your weight and your moisture, that's a dead sign that you've got what's called cross-coupling, which is that the weight is screwing up the moisture and the moisture is screwing up the weight. And by the way, you better believe, while this is going on, the cooking's going to hell. To fix this, we put in a thing called a decouple. It's another advanced control called the decouple. The decouple is a predictive feed-forward control. And what it does is, whenever we alter the basis weight, whenever the basis weight control changes the flow set point, it also makes a change to the moisture set point. Because it says, okay, whenever I change the weight, I'm going to mess up the moisture. So I'm going to make a correction to the moisture in advance. And similarly, whenever there's a correction to the moisture set point, I'm going to alter the basis weight. Because whenever we change the moisture, we screw up the weight. So I'm going to predictively change it back. Decouple is a predictive control. It's a feed-forward control. It's an open loop. There's no feedback there. We can't be sure the decouple works. So decouple is a control that we put in, and it will allow things to control when you have cross-coupling occurring. Okay, my dough is being made in the stock preparation plant, which is in the building next door. It takes 15 minutes from making up a batch of dough to it arriving at the head box. I've got a consistency sensor, which is sensing the consistency, the stickiness of the dough. The thickness of it, if you like, but not the density. Thickness in the not density term. Can anybody think of a way of building a consistency sensor? Well, capacitance is going to be varying more on things like the salt level of the dough rather than the stickiness of the dough. How would you make a proximity work, Max? Matt, you're not far off, though. Infrared's going to be badly affected by things like temperature. Conductivity, once again, is going to be affected by salinity. Nuking it would actually give us density. That is exactly how we would measure the density. And density is going to be a pretty good indication of consistency. So in many cases, yeah, we're going to nuke it. But in this case, there's a better way. Okay, I'll put you out of your misery. This is how we measure consistency. We have an electric motor which drives a paddle. And then there's a couple of things we can do. We can put a spring on the paddle, and by measuring the tension on that spring, we can measure the consistency. Another thing we can do is simply measure the current on the motor. So it's a very simple consistency meter. The nice thing about consistency meters is that they're horrendously inaccurate, so they're very easy to keep, maintained. Right, oh yes, now the consistency is a feed-forward control. The fact that there's a 15-minute delay between the consistency meter and where we want to act on changes of consistency, we deal with that problem by using a history array, which is another one of those first in, first out structures, FIFO structures. So it's a feed-forward system. It's open loop. It's predictive. It's saying, look, the stuff's coming through denser. You need to put a little bit more liquid in. Or it's coming through denser. You need to shut the valve a little bit. So it's predictive control. A feed-forward control. Now, one problem we have with all of these history arrays, and also with the proportional and the integral time, proportional gain and integral time, is that as the machine speeds up and slows down, the length of the history array needs to change to suit the machine. So we use another advanced control which we call the speed retune. And what the speed retune does is it changes the length of the history arrays so that the history array length matches the time delay from the beginning of the machine to the end of the machine. The other thing that the speed retune does is it alters the proportional gain and the integral time, because the proportional gain is based on 0.9 times Tc divided by K times Td. So an integral time is Td times 3 1/3. So as these values, the Td and the Tc, change or can change with the length of time that the donut spends on the conveyor belt, then the integral gain and the integral time are changed to match. So speed retune attempts to retune the P&I values and retune the history arrays to change with the speeding up and the slowing down of the machine. Of course, there's only so far it can go. If you're used to running the machine if you start the machine up and you're running the machine at 100 meters a second, and you speed the machine up to 400 meters a second, the speed retune will not be able to cope, and you'll find that all the P and P&ID values will be completely messed up, and it will need retuning. It's quite common to start a machine up, a greenfield site, for it to start up very slow, and then after a couple of years be running very fast. So retuning is the sort of thing that we need to continually keep doing. We need to be continually thinking about retuning our control loops. Now, when we're talking about P&I values, just as an aside, something you should be aware of. Systems have capacitance and resistance. Capacitors are things that are able to store. Things like tanks. Tanks are capacitors. They're able to store. If we're talking about heat, a large object is able to store heat. Things have capacitors and resistors. In terms of resistors, things that are resistors are pipes, valves are resistors, flow, in terms of heat, insulation around a tank, if we're talking about temperature, is a resistor. So all systems have got capacitors and resistors. Generally speaking, the bigger the capacitor, the bigger the time constant. The bigger the resistance, the bigger the time delay. Although there's a great deal of crossover between the two, generally speaking, objects with control systems that have large capacitances will have larger time constants. And also actually larger time delays. Control systems which have larger resistances will have definitely larger time delays. So when you're looking at control systems, bear that in mind. Finally, to end up with, I'd like to talk about SCADA systems. In the early days, what we used to do is we used to do the DDC control in a PLC, and then we'd have a supervisory control inside a PC. And the PC used to do the supervisory control. DDC used to do, the PLC used to do the simple control. Now, we soon discovered that the PC was a very bad place to do any sort of control at all, because, I mean, this was back in the 90s, and PCs were actually less reliable then than they are now. So we don't do that anymore. Now what we do is inside the PLC, we'll have the DDC control and the supervisory control inside the PLC. We still have a thing, though, that we call the SCADA. SCADA is what sits on the PC. It's not supervisory control so much anymore, except for maybe that's where we'd store the recipes for the donuts. And maybe also there we would do things like stock market access, so that we would decide where we're going to buy our eggs from, that sort of thing, based on the price of eggs in, you know, different parts of the world. SCADA stands for Supervisory Control and Data Acquisition. Supervisory control it gives us nowadays is this sort of thing. It gives us pretty pictures for the operators. It also acquires data so that we get the nice trend plots. And the trend plots, these sort of trend plots, show us, that's not showing up very well, is it? These type of trend plots that show us what's going on with the system so we can get an idea of what the valves are doing and that sort of thing. So SCADA now is a nice set of pretty pictures for the operators with data acquisition, and also as part of data acquisition we also acquire things like alarms to say, oh look, motor 5 has got low oil, or motor 5's gone overheat, probably because it's run out of oil. That sort of thing. So that's what the SCADA system is used for nowadays. Acquiring data for trend plots and alarms and pretty pictures so that the operators can get a nice overview of what's going on and, you know, see what's going on in the system. Okay.